All right. Is that sharing okay?
Yes, looks good.
Okay. So, um, so one of the realities of the world we live in the electronics industry is that through-hole components are becoming harder to find, especially the older parts. Remember back to equipment that you take the cover off and it was all dual inline packages. You plug in the sockets or you solder down, and that's how the thing was built. Well, that was all through-hole parts. And then in the 80s, I remember soldering by hand a 208 pin FPG, or it wasn't an FPGA then, it was it was the IO subsystem for a PC down on a new circuit board design we were doing where I worked. And as time has gone on, it's fewer parts are actually being made available in dual inline packages that you can plug into a socket or use through hole. Everything is now going to a surface mount. In fact, some of those packages are extremely small, which makes them really hard to work on at home. But let's talk about what we can do at home and what makes sense. I'm going to talk about give you an equipment overview of what I've put together. We're going to talk about temperature profiles a little bit and why that's important when using a reflow oven. We'll talk about component sizes, and if you were going to pick a size for a resistor, what can you really handle? An 0201 is, so that's in thousandths of an inch, or maybe it's hundredths, but it, you know what a grain of rice looks like? Well, an 0201 is smaller. So you probably don't want to do that one at home, but there are some reasonable sizes that we can take advantage of. I'll walk you through the reflow process step by step, and you can see how straightforward it is. As an aside, I'll also show you hot air reflow, which uses a hot air pencil. And I'll provide a couple of pages of links to the materials that will reinforce the information I provide in the slides. So here's a view of the two groups of equipment that I use. In the top picture, what we're showing is an Adafruit Easy Make Oven tutorial. The controller module, does my pointer show up on the slide?
Yes, it does.
Okay, great. This is an Adafruit controller that I'll talk about more in a minute on another slide. The oven is $20 from Walmart. It's their bottom of the line oven that works awesome for this application. When you order circuit boards, you can see here in the bottom picture, and I held one up to the camera there a few minutes ago. You know, the boards are 80 cents. I order from JLC. And if you check the box that you want a matching stencil for it in order to be able to screen solder paste onto that board, you check the box and you pay the $7 and poof, they send you one. In this upper picture, that's what this large stainless steel panel is. It's the stencil, and I'll show you in more detail. For solder paste, 50 grams of solder paste ordered from Amazon is $16. And 50 grams will last forever. In fact, it has an expiration date on it, and you're supposed to keep it in the refrigerator when you're not using it. So if you don't use up the 50 grams, well, the flux gets a little thicker, and we can talk about that. Now, you will need some kind of a microscope in order to be able to see adequately. Those just magnifiers built into a lamp, or maybe the headset might work. The viewer. I didn't try one of those, but there are a number of USB cameras available I have a picture later of the small one that I use to take some of these photos. $35 at Amazon. It's adequate for the job. I'll also provide a link for to a YouTuber that has done a comparison of the various inexpensive cameras, looking for one that's reasonable for doing soldering. You're also going to need very good tweezers, so it's worth the investment to get some good tweezers. So here's the Adafruit Easy Make oven. There's a complete tutorial on their website with a parts list. The Easy Make oven, as shown here, this is made out of an Adafruit Pi portal. It's not PI Pi, it's PY Pi. It runs CircuitPython. The application is written in CircuitPython. And I wanted to learn CircuitPython anyway, and this was a good introduction to that whole process for me. There's a little optional stand, which is what it's standing on. There are two extra parts. One is this relay module. I showed this a few years ago in another Nerdfest presentation as an example of off-the-shelf hardware that's available for deployment on mountaintops and things like that. But it turns out it's the exact thing I needed for this project. There's also a thermocouple. It's a Type K thermocouple, and they suggest taping it to a circuit board so that the temperature that is read, you can see it down here on the left, it's currently showing 154 degrees C, so that the temperature that's being read is representative of the temperature on the board that you're actually soldering. So I just took a piece of scrap PCB and taped it down. No, you don't just grab blue tape or masking tape. You need Kapton tape, which is a polyimide 750 degree Fahrenheit kind of tape. And I provide a link to that later in the slide set. So that's it for the Reflow. It's very simple. It plugs together very easily, and it came up and worked after I got the you follow the step-by-step instructions that are on the learning pages of the Adafruit website, and it just comes up and works. So let's talk about soldering temperature. What if you wanted to make some toast for breakfast? Well, the algorithm for making toast is pretty simple. You turn the oven on at full temperature for a fixed amount of time, and when the fixed amount of time expires, then it turns off. So it's a pretty linear temperature ramp until it gets up to, for medium toast, it's about 350 degrees Fahrenheit. It's amazing what you can find out on the internet using a Google search, and then it cools off. So that's the profile for something simple, like if you just turn the oven on and leave the oven on. But in our case, especially the integrated circuit manufacturers are very specific about the profile that they want their components to understand. In other words, you don't want to thermally overstress the part. You want to make sure that the flux and the solder is distributed properly during the process. And then you want to make sure that it cools down at a reasonable rate. So there's a preheat process, and the preheat process is used to evaporate any solvents that might be on the components or on the circuit board and get everything up to sort of a starting temperature. And everything will be at the same starting temperature then. Then there's a soak process. You can see that here in the middle, where it soaks all of the components and the circuit board and the solder and the flux, and it brings it all the way up to and through the melting point of solder. This green line shown here is the recommended profile for 6337 solder. Lead-free solder would be a different profile. The controller will turn on the oven. That's this red line. The red line is the monitoring of the thermocouple as the oven heats up. This bright red dot up here in the corner is the oven is on at this time. When the temperature gets to a particular level, the controller can turn the oven off in order to keep it close to the profile time and temperature. And then it'll turn it back on again to go through soak. And then as it goes through 183 degrees centigrade, the solder melts, and that's the reflow process. So in this upper right picture, you can see that from 183 up to the maximum temperature of the profile, it will continue to soak and then reflow the parts. And once it reaches that maximum temperature, the oven is turned off, and there's a beeper on the pie portal controller that beeps as a request to you, the operator, that you open the door. Opening the door is what implements the cool down process. And you can see that it cools down actually pretty quickly just by opening the door. So that brings it down, and once it's cool enough, of course you don't want to burn your fingers, so I use an infrared thermometer, one of those with the laser in it. You point it at something and you know what the temperature is. I use one of those to make sure the circuit board is down under 100 or so degrees Fahrenheit, so that I can safely pick up the boards and remove them from the oven. The results of that are surprisingly good, and I say surprisingly, but it's science, it's physics. This is what they tell you to do, and this is a little bit of a blurry picture taken with my phone, actually, that shows the relative sizes of the components, and I'll talk more about the shininess of the solder connections a little bit later. But 0805 is a reasonable size to install by hand. The parts are easy to see. With tweezers, they're easy to grab. This transistor over here, this is just like a 2N3904, except in a standard package, and pretty much the standard package for FETs and transistors in this size. You can get them a lot smaller than this, but in this size, there's SOT23s. I find that a very convenient size to place in position. The U1 here, this is an SO16 part. You know what a 0.1 spaced header looks like? Well, those are 0.05 space pins. So it's like having two pins in the space of one on a header. So you just set them down. Don't drink a lot of coffee so you're not shaking, but set the part down, tap it with the tweezers to get it close, because it's surprising how well the solder will, as it melts, will pull the thing right onto the solder pad. I do stick to through hole for LEDs. LEDs are using surface mount LEDs and then a light pipe and trying to get the light to come out the front panel. It's just way easier to use through hole LEDs, and King Bright and Dialight and all those guys continue to produce through hole LEDs. And headers and connectors and jumpers, always use through hole parts. I've seen cases when I worked at HP. We had a prototype board a $50,000 board that had a 3-pin header on it to monitor I2C, and somebody pulled the probe lines off the header, and up came the socket along with the traces on the board. That you just need the mechanical stability that through-hole parts bring for headers and connectors. So I'm going to walk through the process step by step here, and to tell you what each of these pieces are and how to take advantage of those. So starting way over on the left, there's the stainless steel stencil that comes from JLC, $7. The reason it's so big is when they come in a standard size, and it's because they fit a machine that when you're doing high level production, it automatically does the spreading of the solder paste. In our case, we're only using a little bit of it. So what I do is I take some scrap PCBs and some blue tape, and here in the center you can see that I've put down one of the boards that I'm going to solder. I push in the boards to hold it firmly in place, and then use blue tape to secure them. So what you do is you basically lift up the stencil, put a board in it, lay down the stencil, as shown up here in the right corner. And there's a close-up of the holes in the stencil for this particular circuit board. You can see that we don't see any green through there because it's nicely aligned on the pads. So now we're going to put on the solder paste. The solder paste is really pretty easy. This is 50 grams. You can see this goopy gray mess. If you zoom in with a microscope, what you see is what this center picture shows. Those are little solder balls, and they're suspended in this case, no clean flux. And the no clean flux will, it holds all the solder balls in position, and then when it melts, it helps to make the solder flow during reflow. Up here in the right corner, you can see we use a squeegee. My squeegee happens to be an old gift card or something. I have one. Here's a credit card. You just put some of the paste either on the squeegee or on the stencil, and you draw it across to make sure that all of the holes fill in. You can see here where I did a first pass, and you use a lot of paste to start. You really smear it on so that you're filling up all of the holes in the stencil, and then you draw back across it. Usually you go maybe left to right or top to bottom or at an angle, but you want to make sure every crevice is filled, and then you scrape it all clean. So on this way over here on the left, this is a bare board, and the more green picture is you can actually see the solder paste. I took that with my phone, surprisingly, but it gives you a pretty good view of the thickness, which is about 1/10 or 1/8 of a millimeter. There's not a lot of that stencil is pretty thin, and that's all the solder it takes. In order to put down the parts, I happen to have a Meiji binocular scope, but you can use a USB scope and put it up on a large monitor to make it very easy to view the board. This picture on the right was taken with that USB microscope, and actually you have to get the lighting right, and as long as you have the lighting right, you can actually do a pretty good job with it. You can see this part I placed is centered up, and using the tip of the tweezers, you kind of press it down into the solder. You can see the capacitors. These are 0805 capacitors here that are pressed in. And that little misalignment to the pads, that's fine. They'll straighten right up when the they go through reflow. So the reflow process, I do 4 at a time because that's a nice size for the oven. See the thermocouple here in the back. I press start on the controller and I watch it happen. I hang around waiting for the beep so I can open the door. And then you let it cool down. So be sure to allow it to cool before you reach in. And you can see how shiny the pads are. This is pretty good. This is pretty good.
2 minutes.
Okay, the pads are nice and glossy. And that little bit of solder paste, remember this is no clean solder paste, so you really don't have to worry about it. And then you want to clean up. You want to use 99% the technical isopropyl alcohol, not the stuff from Walgreens. That stuff's got oils and things in it, and it'll leave a residue. This gets it nice and clean. Make sure you clean out the holes in the stencil. And a quick introduction to hot air reflow. This is a lot of these reflow pencils are really expensive, hundreds and hundreds. Well, this is $70 on Amazon, and it works really, really well. There's lots of examples on YouTube of how to use this for rework, like if you had to change out one part, or if you had to do a whole board. That knob is for the blower speed. If you got a lot of little parts, don't turn the fan up too high. You don't want the parts to blow away. So here's the list of references. Here's the picture of the small USB microscope that works pretty well. So here's a link to a microscope comparison. Here's the link to the high temperature tape. It's worth having some maybe 1/2 inch wide tape around. And
offering to wash windshields for change at crowded intersections and selling food and flowers.
somebody needs to, thank you.
I got it.
And components, go to eBay, find the resistor and capacitor SMD sample book for 0805s and order it. They're $30 and you get 50 of each value. That's a screaming deal. And especially if you only need a part here and a part there. Here's the link to that pencil, and be sure to search around on YouTube. There's tons of stuff on reflow soldering. Now I use the Adafruit make oven, easy make oven, because there was no modifications to the oven itself. It's plug and play. Doug had an old one he gave me as a backup. And as long as they can reach 600 degrees or 600 degrees Fahrenheit or so, you can be successful with whatever you have. Don't use it for toast afterwards. Once you use it for electronics, do not use it for anything else. Do we have any questions?
Yeah, Roger Oakey, W3MIX. How stable are the parts once you place them? Are the parts stuck enough to be able to move the board around carefully without dislodging them before they're soldered in place?
Definitely. I put them, I have a cardboard tray, and I usually stuff 4 boards at a time and set them out in this cardboard, and I can very easily just, walk to the other end of the basement where my soldering station is. One of the things I didn't mention, by the way, it's in front of a window, so if the fumes are too much, I just slide the window open and I'm good. But I have not noticed a fumes problem doing it this way. Any other questions? Anybody else?
So Bob asked the question, any tips for applying paste for hot air rework?
There are 2 ways to do it. One is You can use a stencil if you're doing a whole board, but to do a single part, you can buy solder paste in a it looks like a king size hypodermic needle. They come with 5, 10, 15 grams of solder paste in them with a very small needle tip. And you can squirt that along the pads of the device that you're going to solder. You can then place, and don't worry about keeping the solder paste on the, let's say you're doing one of these SOIC 16s, you just stream it right across all the pads, just a small bead of it, set the part in there, use hot air, and the solder will wick to the individual pads. Maybe you'll have a short when you get done, but generally not. Generally, it'll come out just right. There's some great videos on how to do that. One of the keys seems to be to use a lot of flux to make sure that the whole area is almost swimming in flux. That seems to help a lot.
Chris, A5IT asks, some of the PCB fabs will do assembly. Would you consider letting them do the common components and you only have to do the rarer stuff at home?
Yes. I debated doing that for this project where I just let JLC do the assembly. They have what's called a basic library of parts. The basic library has 500 or 600 parts that are always on their machine, so they don't charge you a mounting fee to mount a reel of whatever it is you want to install. So if you stick with the parts, and it's resistors and capacitors and that kind of stuff, if you stick with those parts, then the board comes assembled for about $2. It's crazy inexpensive to let them do it. I will be experimenting with that. What I needed to do was take the output of the KiCad bill of materials and put it in JLC's format, and I wasn't at a point where I wanted to do that, so I learned to do it this way instead.